Hello everyone, I want to use this video to go over lecture number 2. In this lecture, we are going to study location and map essentials. First of all, let me present it. In this lecture, we are going to study Earth and how we map our Earth. So first of all, I need to share with you this amazing picture about our Earth. This picture gives you the real shape of the Earth. It's like an ugly potato, isn't it? Well, I didn't call it ugly potato. Actually, here, NASA called it ugly potato, post-stem gravity potato. So the real shape of the Earth, if you only consider gravity, okay, our Earth's surface actually is very irregular. So that's the keyword on this slide. The real shape of the Earth is irregular. It's not smooth at all. But as geographer, we need to study it, right? So an easier way is to use an ideal shape like a ball or an oval shape to approximate the real shape of the Earth. Okay, so I want you to make connection between those two. The globe you see in our labs, in your house maybe, well, it's not the real shape of the Earth. It's approximation of the real shape of the Earth. Okay, but let's just make our life easy. The size of this ideal ball, okay, you can see the polar circumference is different from equatorial circumference. Well, you say no big difference, right? But there are a little bit different. You can see this one equatorial circumference is a little bit longer than the polar circumference, right? So which makes sense if you cut the Earth, like you cut a watermelon or something, right? Okay, it's an oval shape. It's not round. Okay, so the round or the globe is more approximation. Okay, you happening over there. So why is that? Because the Earth is spinning around its own axis. Okay, that axis is connecting North Pole and South Pole. So when you're spinning something, okay, around like you're spinning like your chicken, right? You will feel that force. We call that centrifugal force. So that basically will throw the gravity, push the gravity more concentrated at equator. Okay, so we call that equatorial bulge. That is also why equatorial circumference is a little bit longer. Okay, you also see that on our ugly potato. You can see this the bulge, right? So that is along the equator. Okay, so here is the ocean. Okay, we're talking about the land masses right here. Okay. All right. So well, then the globe, right? And then on this globe, the number one thing we need to do is to locate our certain location, right? We locate a point. So for example, I want you to study Red Sea, okay, or some place in Egypt. Okay, the pyramids. Okay, where it is. You say, oh, I can give you the longitude and latitude. How you define longitude and latitude? That is our geographic grid. Okay, so basically, this geographic grid is this fishnet cover the entire Earth. And you can see you have those horizontal lines, you have those vertical lines. What are they? Well, horizontal lines, you can see they all parallel, right? They are parallel, but those lines, those vertical lines, so-called vertical lines, they converge at the North Pole and South Pole. Well, they all parallel with the equator, right here, equator. So we call them parallels. And those converging lines converge at North Pole and South Pole. We call them meridians. Meridians. Okay, it's not longitude and latitude yet, but before we define before we define that, we need to know what are the parallels, what are the meridians, and you put them together, you have these grids, and each intersection between one parallel and one meridian, that is your location. Okay, so that is your location. You can pinpoint any place on this earth, on this fishnet, on this geographic grid. Okay, you don't have to just draw those lines. You can draw any lines as long as it's parallel to equator, it's parallel. As long as converge at North Pole and South Pole, it's meridian. Okay? Alright, then what is longitude and what is latitude? Okay, so we use parallel to define our latitude. Okay, so parallel circles running east and west. Okay, with the same latitude. Okay, equator, well, that is an imaginary parallel or imagined circle cover across the center of the earth, right through the center of the earth. Okay, that's the longest parallel, dividing the earth into northern hemisphere and southern hemisphere. Then what is latitude? Latitude is your parallel. For example, this 30-degree north, right? How far it is from equator. We are not using this distance. We use this angle. So you can see, if you can draw a line between the center of the earth to your parallel, for example here, you will form an angle, and this angle is 30-degree north. Okay, and then what is 60? 60 is you draw a line between center of the earth to this point, and then you can measure this angle, that is the 60 degree. Okay, we're not measuring this distance, we're measuring this degree, and 90 obviously is this angle. Okay, and you can see latitude can only run up to 90 degree. Measure from the equator. Okay, all right. Okay, so make it simple. Latitude is the name of the angle, the degree of the angle, and parallel is the name of the line. Okay, all right. Okay, so you can see this is one figure from our textbook. Okay, this equator, and how far you are from equator by angle, that is your latitude. Okay, oh, it's actually very easy to memorize the name. Latitude, like ladders, right? You climb up to the northern hemisphere or climb down to the southern hemisphere. Okay, that is how I memorize it. Latitude, ladders, latitude. Okay, so why it's important? Well, the zone of the latitude is specifically important if we talk about temperature. Okay, so you can see when we study this area, we know that is close to equator, very hot. We call them tropics, right? So you can see how we define tropics. We use latitude degrees to define tropics, between 23.5 degrees north and south. Okay, and subtropics, that is between this degree 23.5 to 35 north and south. Okay, mid latitude, that is 35 to 55. 55 to 80, that is high latitudes, and beyond 80 to 90, that is polar. Okay, they applied to both hemispheres. Okay, so you can see zone of latitude is important when we talk about temperature, and different zones, different landscapes, different vegetation, right? Okay, all right, so then longitude. What is longitude? Longitude defined by meridian. So you can see those are the meridians, right? But we need to, like our latitudes, we need to choose a starting point. Latitude starting point is equator, right? But longitude, meridians, we don't have a very special line which we can start from. So all people on the earth, we agree, this is the convention, okay? Starting from this line cross North Pole and South Pole, obviously, and also cross Greenwich, England, okay, right here, this black line, we call that 0 degree. So if you're facing to this 0 degree on your right hand side, that is our eastern hemisphere. So you can see all these with E, right? Okay, to the left hand side, that is our western hemisphere. So you can see all with W. So you also need to do that. W, western hemisphere, use E to indicate eastern hemisphere. Okay? And how you measure this degree? Very simple. From this line, from prime meridian, this 0, okay, to your meridian, what's the angle in between? Okay, again, we use angles. Okay, all right. So same thing on our map. So you can see if you want to locate. Oh, this should be E. I don't know what's happening there. Okay. On your map, first need to find your starting point. Okay, this is X, equator, right? This is a Y, or prime meridian, past Greenwich, England. And then you can see above the equator, that is northern hemisphere, and we're using degree again. Don't measure the distance, okay? Because distance will be different, but angle will be always applied, okay? And then here you can see southern hemisphere, same thing, okay? From here, prime meridian, to the right hand side, eastern hemisphere, and you change this O to E, okay? And here, the western hemisphere, that is W, okay? And if you locate, you just find your intersection here, okay? Cross. Okay, so that is longitude and latitude. That is very important concept in this lecture. Number 2 is, well, as geographers, we use maps more often, right? So one of the jobs is to flatten this 3D sphere, the 3D sphere, our globe, our Earth, to flat. But it's very difficult, guys. For example, if I ask you to flatten your orange peel on the table, you probably end up with this or worse, right? Okay, so you can see because 3D we have one more dimension. It's impossible actually to flatten your 3D globe, 3D sphere to a flattened surface in which you don't have those gaps. Okay, it's impossible to flatten a peel of an orange into a nice connected rectangle. Okay, so which means on our Earth surface, on our map, you have a lot of places. If you see down on the map, you have a lot of distortion. For example, here, this is where? This is Greenland. Greenland, you can see on our map, is the same size as South America, but actually it's not. In our lecture, let's play with this true size. You will see actually it's 1/8 of it. Okay, why? Because when you flatten your orange peel, in order to make a rectangle, you need to stretch it, right? You need to stretch it. So that is why Greenland is so large. Okay, so that is distortion. So on our map, you have different types of distortion. Okay, you have two categories in general. You have size, you have shape. So here's the dilemma. Okay, you can only keep one thing right, either size or shape. If you keep size right, okay, we call your map equivalent map. If you keep your shape right, we call that conformal map. So it's impossible, it's a dilemma. Okay, you cannot keep both true. It's impossible to have a map that is both conformal and equivalent. It's impossible. Okay, then how to judge? How to tell your map is equivalent or conformal? Look at those circles. We call that T-sort matrix. Okay, well, distortion matrix. So you can see those circles, when they at equator, they're circles, right? There are circles everywhere. Even you enlarge Greenland, you can see still circles. You just see increase the size. So this will be a conformal map. Okay. How about an equivalent map? You can see circle at the equator. When you go to the two poles, that become oval shape, right? So that is in order to keep the size true, you need to sacrifice your shape. You need to distort your shape. Okay, so that is the T-sort distortion matrix you see on the equivalent map or equal area map. Okay, all right, and then how about you say, oh, I want to more or less keep both more or less right, okay, almost right. Well, then you sacrifice both. You could sacrifice both. We call them compromised map. Okay, so you can see here, that probably is what you see in your high school, right? They only for show because you have so many distortion, right? Okay, so this is three map distortion: compromise, equivalent, or conformal. Okay. All right, then another question is how you flatten this 3D globe to a 2D flat surface. Okay, I bet you played this game when you were a kid, right? We call that hand shadow, right? So you can light up your candle, and then you can cast your hand, which is 3D, the shadow to a flat surface, right? Like on your wall, that's the shadow. Okay, so here we use the same idea. Imagine we have a light bulb inside the earth. When you turn on the light bulb, you can cast the shadow of all the parallels and meridians on a flat surface, right? So this flat surface with the shadows, that is your map. That is your map. That is how we turn 3D globe to a 2D surface. We call that map projection. We have three types of map projection. Depends on your flattened surface. Okay, so if this flattened surface is a cylinder like this, we call that cylindrical map projection. So basically, you wrap up your Earth with this cylinder, and you turn on the light. You can cast the shadow on this cylinder, isn't it? Can't you? Right? Okay, then you unfold, you cut it open like you open a burrito or something. You can flatten this cylinder to a map, to a rectangle. So voila, that's your map. Okay, and then you can have this cone shape surface, right? You give it at you use a cone, cover the top of the earth, for example, and you cast the shadow on this cone, and then you can cut it open, flatten it. That's your map. Call that conic map projection. Okay, and of course you can just use a piece of paper. Okay, we call that azimuthal planar map projection. Okay, like this. Okay, don't get me wrong. You can place this paper any place on the earth. Can be North Pole, can be South Pole, can be Santa Monica, can be anywhere. Okay, but keep in mind this point is important. On this cylinder, this line is important. This red line. On this conic, this red line is important. We call them standard line or center point. Okay, so that is a line touch the earth, touch the earth, touch the earth. You don't have a distortion. You don't have shadow. Okay, in this video, in this story map, I'm going to share with you a story of map projection and why all maps are wrong. Okay, so let's do that in our lecture. Okay, so the next concept is small circle and great circle. So what's that? Let me share with you the definition first. Great circle is a line, is a circle, right? Okay, that bisects, cut the globe into two equal halves. But that's called bisects. Okay, into two equal halves, such as equator. Okay, but you don't have to just use equator. You can also cut, cross North Pole and South Pole. Right? The vertical one is also a great circle. So as long as when you cut the Earth fairly, evenly into two equal halves, then that circle is your great circle. Okay, but this one is not great circle. You can see one part is smaller than the other. You're not fair, so that is your small circle. Okay, so why this matter? Because a great circle, when you travel over the Earth's surface, great circle actually represent the shortest distance between 2 points on the Earth. Okay, geometrically. Okay, so for example here, if you want to travel from, let's see, for example LA, okay, to China, okay, to China, from LA to China, I don't have that here, London to Seattle, okay, so, well, actually the straight distance from between Seattle and London, let's see that on globe, Seattle is about here, London is about here. You can see the straight distance actually is beneath the Earth's surface, right? Your airplane cannot fly beneath the Earth's surface. Okay, well then how to find the shortest distance? Well, you need to connect the circle, connect the two locations and use the great circle distance. So you can see you need to fly all the way to Greenland, to Iceland, and then to London. This is the shortest distance. Okay, we call that great circle route. So you can see here on our map. Okay, this route probably on the globe is like this. Okay, it's like this circle. Okay, more or less. But you can see when you see that on the map, it's not the shortest on our flattened surface, right? That's another example. Your map is lying to you, this map. This is called Mercator projection, as you can read in your textbook. It's a conformal map projection. Okay, it's a conformal map projection. They keep the shape true. You can see it's still a circle, but distort the size, distort the distance. Okay, and this straight line distance, we call that ram line on Mercator projection. What's that? That is, you keep the same angle. You keep the same angle to the north. Okay, so you can see here, maybe this angle is, I don't know, maybe 90 degree, 85 degree. Okay, this is also 85 degree from this 100 degree west west meridian. Okay, so here this angle, oh, and this angle, and this angle, and this angle, they all same. Okay, we call that ram line. Okay, it's good for navigation across the sea when you have the good old-fashioned compass. Okay, but you can see this map projection, that is our mnemonic map projection. We actually distort the shape of our great circle route. Okay, so great circle route is the shortest distance, but don't be fooled by your map. Alright, so another important concept is your map scale. How far is it? Okay. Map scale, like last lecture, I was trying to find this definition. It's right here. It's actually the relationship between distance on the map and the corresponding distance on the ground. Like last lecture, I shared with you this 1 inch you measured on the map represent this many inches on the ground. Or you can use centimeter. 1 centimeter you measured on the map represent this many centimeters on the ground. Okay, so that is a ratio. So here, last lecture we studied this already. Okay, small scale, that is means this ratio is small, but you see more area, right? You see more area, but this ratio is large because 1 inch can only represent this many inches. If you convert it equals to less miles or less kilometers, that is why you see smaller area. Okay, all right, so we're talking about the ratio here. Okay, so in our lab, you're going to do the calculation. So let's do that in our lecture. I'm going to share with you some examples about how to use this ratio to calculate the distance. Okay? All right. Okay, So the last but not least, another thing we want to map out on our Earth surface is our terrain, mountains and valleys, highs and lows, right? Oceans. Okay, how we map that? We call those mountains down, mountains, valleys, we call them relief, the distance, the elevation distance. You can see this is a relief map, called a topographic relief map, terrain relief map of California. It's beautiful, isn't it? We are living in a beautiful state. Okay, all right, and how we map that? Topography is the shape and physical characters of the Earth's surface. Okay, and elevation is the vertical distance measured from mean sea level. Okay, then relief is the distance, is the difference in elevation. Okay, vertical distance between two or more points on the Earth's surface. Okay, so areas with low relief, we call them flat. Areas with high relief, we call them mountains. All right, then now how to measure that? We use this concept, we call that contour line. So what is contour line? Contour line is the line, the solid line, okay, connecting the points with the same elevation. Okay, what is elevation? Vertical distance of a land surface above or below the mean sea level. Okay, so measure from sea level, you have the same elevation like here, that is 2,600 meters. You connect those points. Okay, you draw those points. You can see I connect all these points on my mountains. Okay, then you do what? You flatten it, just like you flatten your clasp ball for your dog. You know, if your dog have a ball, you can clasp it, you can hang that on your backpack, right? So this is what you see on the map. Well, basically, yes, you see all these lines from the top down, okay, straight down. You see those circles, right? Okay, so it's interesting. Yeah, it is interesting. You can see on this side of the mountain, right? You can see those contour lines are very busy. That indicate actually here elevation change very, very fast across horizontal distance, right? So that means what? A very steep slope. Okay. On the other side, you can see it's flat, it's gentle, right? It's not that steep. Well, you can see those contour lines, the spacing is wide, right? Okay, so that is how you tell the relief, the terrain, the topography, the shape of your Earth surface. Okay, it's steep or it's flat, it's gentle. Okay, so we are basically looking at the distance, the spacing between different contour lines. Okay, all right, and also the shape of those contour lines, when you flatten it, can also tell the shape of the mountain. For example, this like beautiful volcanic cone, okay, volcanoes, okay, they're like cone shape, and you can see when you draw the contour lines on your mountain, you flatten it, you see it from the top, you can see here. It's like they share the same center, right? Okay, those circles. You can tell, oh, that is a cone shape like mountains. Okay, and here show you the real topographic map. You can see here it's very steep, right? And here it's very shallow because the spacing is wider than here. Okay, in our lab we are going to use those contour lines to explore our Yosemite, and you are going to climb Half Dome. Tell me which side is gentler. Alright, so that is all for this lecture. Let me go back to highlight the key things. Okay, so we first, our globe is an approximation of ugly potato. Okay, and our Earth's equator have a larger equatorial bulge. Equatorial circumference is longer. Okay, then very important, you need to know what are the parallels, what are the meridians, and how you use them together to pinpoint a location. use those degrees, longitude and latitude, how they define that. Okay, and then why it's important to study latitude. Okay, because temperature. Oh, why it's important to study longitude? Because of time zones. Okay, in your textbook you will read it, but because it's simple, I just leave that for you. Okay. All right. Okay. So then another concept is our projection. Okay. So first you need to know 2D map. You have a lot of distortion. Okay. You have different type of distortion. Size true equivalent, shape true conformal. If you sacrifice both, that is your compromised map. Okay. And how you convert this 3D to 2D. Okay. You use this projection idea. Okay, turn on your light bulb, cast the shadow of your parallels and meridians. Okay, and one point is very important. Standard point lines is important. Standard line because no distortion. Okay, and you need to know the difference between great circle and small circle, and don't be fooled by your maps. Okay, and very important, how to calculate map scale, how to use map scale to calculate distance. Okay, you're going to practice with your lab question. Okay, and then what is topography, what is elevation, what is relief. Okay, and how to use your contour lines to tell the shape of the Earth's features, topography. Okay, so let's practice in our lab, and I will end this lecture presentation. Bye for now.